Hi everyone, welcome to our online class on electricity and electronics at Paradise Business and Technology College for the academic year 2026. It's a free online course. The class coordinator is Mr. John Cooper, which is me. The duration of the course is 4 weeks. This is the experience and qualification I have obtained and acquired throughout my years of work and in the industry and in the teaching field. My name is Mr. John Cooper. I'm the course coordinator. I have a bachelor degree in physics, electronics, and instrumentation from PNG University of Technology. I also have level 2 qualification in training and assessment. I also have a CASA PNG training authorization number when I was with CASA Agatec Aviation College. I was also a AutoCAD trainer at Don Bosco Technological Institute. I also attended OHS level 1. I also attended safety training when I was with Paradise Food for a part-time role. My work experience, I was with Asia Pacific Aviation Department at OLA, opposite PNG Power. I was an instructor and lecturer at Agatec Aviation College. I was electrical maintenance engineer at Atlas Steel PNG, Baroni. I was instructor at Don Bosco. I was an electrical instructor. I was also an electrical supervisor at Pacific Industries 6 Mile Pepsi. I work with one of the local engineering company, Green Dot Energy. I was able to work under one of the senior engineers. I was also a part-time electrical shutdown technician at Paradise Foods Limited in 2021. So these are all my qualification and work experience. In the course of electricity and electronics, these are all our units, the course outline. We have total of 17 units here to cover in this short course program. We have Unit 1, Measurements and Electrical Safety Fundamentals. Unit 2, we have Fundamentals of Electricity and Circuits. Unit 3, we have Ohm's Law, Energy and Power in Electronic Circuits. Unit 4, we have series circuits and voltage management. Unit 5, we have parallel circuits and current distribution. Unit 6, we have advanced series parallel circuits and network theorems. Unit 7, we have magnetism, electromagnetic devices or electromechanical devices. We have Unit 8, we have alternating current, AC, fundamentals and waveform analysis. In Unit 9, we have capacitors and their applications. Unit 10, we have RC circuits or resistor capacitor circuits, sinusoidal response and analysis. We have inductors and their applications. We have RL circuits or resistor inductor circuits, sinusoidal response and applications. We have RLC circuit or resistor inductor capacitor circuits, impedance, resonance and applications. Unit 14, semiconductors and diode applications. Unit 15, transistors and application. Unit 16, we have operational amplifiers and applications. Unit 17, we have logic gates and digital circuits. So these are all the 17 units we are going to cover in this course. We have assessment for each course, and then we have the marks for each of the quiz that we are going to sit for in this short course. In this video, we are going to look at the first chapter, which is measurements and electrical safety fundamentals. We are going to look at the quantities and measurements in science and specifically in the field of electricity and electronics. Okay, the first topic that we are going to discuss is physical quantities. Physical quantities are very important to discuss, because in any field in engineering, science, and technology, physical quantities forms the basis of these fields. So in order to understand electricity or any science subject, electronics, you need to understand physical quantities. Physical quantities form the basis of any engineering, trade, technology, or science field or subject. Okay, what is a physical quantity? Physical quantity or physical quantities are measurable properties of a physical system comprising of a numerical magnitude and a unit. Example, 2 kilometer. 2 kilometer talks about length. 2 is the numerical magnitude, kilometer is the unit, and it's referring to a length. Length is a physical quantity. They are fundamental for describing physical laws and are divided into basic quantities or base quantities, and there are seven basic quantities like length, mass, time, current, temperature, amount of substance or mole, and luminous intensity. These are the very 7 fundamental physical quantities in which all other physical quantities are founded on. And on this, from these 7 basic quantities, we have derived quantities like speed, force, energy, density, area, volume. These are all derived quantities. They are derived primarily using the international system of units. So we have 7 basic quantities, and from these basic quantities we have other derived quantities. Key classification of physical quantities: we have base quantities. The 7 fundamental base quantities, they are independent quantities that form the foundation of physics with SI units, and they are length in meter, mass in kilogram, time in second, electric current in ampere, temperature in Kelvin, amount of substance in mole, and luminous intensity in candela. These are 7 basic fundamental quantities. From these 7 basic fundamental quantities, other physical quantities are derived from these basic quantities. Derived quantities are defined by combining base quantities through physical laws such as area. Area is length times width. So length is measured in length, width is also in length, so length by length. So that's why we have meter square for area. Velocity is distance on time, which is meter, length on time in seconds, or meter per second. Force is mass times acceleration, and mass is kilogram, acceleration is meter per second square. So the base unit of force is kilogram meter per second square, where it is derived from this basic quantity. Mass, length, time are the basic quantities of force. So force is derived from mass, length, and time. Density is mass over volume. Volume is derived from length as well. So density is derived from mass and length. Components of a physical quantity are complete measurement consists of 2 parts: the numerical magnitude, the number that indicates how many of the unit are present, example 10. Unit, the standard used for measurement, example kilograms. Okay, basic electrical quantities. Basic electrical quantities are fundamental parameters used to analyze and design circuits, including voltage, potential difference, or sometimes they say electromotive force, EMF, current, which is the flow of charge or electrons, resistance, opposition to current, flow or flow of charge, power, energy usage rate, or the rate at which energy is used in a circuit, and the charge. Key units are volts for voltage, amps for current, ohms for resistance, watts for power, and coulombs for charge, respectively, governed by the Ohm's law. So these are the basic physical quantities in electrical, electronics, and electricity. Okay, let's look at the basic definition of these basic electrical quantities. Voltage, V or E, sometimes denoted as E, is a force, electromotive force, or voltage is a force that drives the electrons to flow through a circuit. So it's measured in volts. This is the electrical potential difference or push that causes charge to move, and is defined as energy per unit charge. So voltage is equals to energy over charge, or according to Ohm's law, you can say current times resistance. So voltage is basically a force, electromotive force in a circuit. So why is electromotive? Because it moves electrons, pushes electrons to a circuit. Electro means electrons, motive means motion, and force meaning push. Okay. Current I, measured in amps or amperes, is denoted by A. This is the rate at which electric charge flow through a boundary, calculated as I is equal to charge on time. Okay, when the charge moves in a flow through a circuit, then there is resistance. Resistance is measured in ohms. This is the opposition to the flow of current or charge, calculated as resistance is equal to voltage or electromotive force divided by the current through the circuit. Power P, measured in watts. This is the rate at which electrical energy is consumed or produced. So power can be the power that is required by an appliance, or power that is generated by a power source. So watts on the load side and kVA on the generation side. Later when we come to electricity generation and all this, you will differentiate between the watts and kVA on the generator and all this. Charge Q, measured in coulombs. See, this is the basic property of matter that causes electrical phenomena. Charge, electric charge, or charge is equals to current times time. And then we have energy. Energy can be different types of energy, but in this study we are specific. It's gonna be electrical energy, measured in joules. It's representing total work done in the circuit. Okay, so that's electrical energy. Additional electrical quantities that we are going to discuss. Conductance, G, measured in Siemens, is the inverse of resistance or reciprocal of resistance. So the higher the resistance, the lower the conductivity. The lower the resistance, the higher the conductivity of a material. Capacitance is measured in farads, the ability to store charge in a circuit. So capacitance. Inductance, L, measured in henries. H, the ability to store energy in a magnetic field in a circuit. And then we have frequency, measured in hertz, the number of cycles per second of an AC signal. We also have impedance. It's one of the another electrical signal. It's the total resistance in a circuit, including capacitance, resistance, and inductance. And we also have the admittance, which is the inverse of impedance. Okay, let's look at the different electrical quantities, their symbol and their formulas. Basic electrical quantities, we have capacitance, symbol is C, SI unit is farad. The symbol of unit, SI unit is F. Charge, the symbol is Q, the unit is coulomb, the unit of symbol of the unit is C. We have conductance G, measured in Siemens, and the symbol of unit is S. Current I, measured in amperes. The symbol of amperes is A. Energy or work is W, or electrical work or electrical energy, that's the same thing. It's measured in joules. And then we have J. Frequency, F, it's measured in hertz, the unit is hertz, and the symbol of the unit is Hz. Impedance, Z. Ohms is the unit, the symbol of ohms is that omega there. Impedance is the total resistance, inductance, capacitance in a circuit. And then we have inductance, L, measured in Henry, the ability of a circuit to store magnetic field, charge in magnetic field. We have power, P, measured in watts, and the unit of the symbol of watt is W. We have reactance, X, measured in ohms, and we have symbol is omega. Resistance R, and we have the unit is ohms, and then we have symbol of ohms is omega. Voltage V, volts, and symbol of unit volts is V. Okay, furthermore, electrical quantities with the formulas: charge, current times time. Current is the inverse, the other way around of charge. Current is equals to charge on time. And then we have energy, or work done in a second, or electrical energy is power times time. It's measured in joules. Power is work on time, or electrical energy on time. It's measured in watts. Or resistance, we have R, ohms. According to Ohm's law, it's voltage over current. Voltage is volts. It's work or electrical energy over charge. Or in Ohm's law, we say current times resistance. Inductance, it's measured in Henry, L. It's the magnetic field divided by current. That's phi over pi, or phi on current. We have capacitance C, farads, measured in farads, and then it's charge on voltage. Frequency F, measured in hertz, and that's the inverse of time, or time is the inverse of frequency. Impedance Z, ohms, and it's voltage over current, or total voltage in a second divided by the current, including the unreal and the real components, imaginary components put together when we are talking about impedance, because the capacitance and the inductance are also included. But later, when we look at RC circuit, we're going to discuss impedance, admittance, and all this. Admittance is the symbol is X, and we have ohms. The formula is voltage over current. Okay, these are the basic quantities and their formula. Electrical quantities and measurements. Current is measured by ammeter. Voltage is measured using voltmeter. Power is measured using wattmeter. Resistance is measured using ohmmeter. Capacitance is measured using capacitance meter. Inductance is measured using inductance meter. Frequency is measured using oscilloscope. Period or time is measured using oscilloscope. Charge is measured using charge meter. Conductance or conductivity is measured using conductivity meter. So these are all the electrical devices used to measure these electrical quantities. But with the multimeter, the latest multimeters, you can measure all these quantities using just one meter, and that's why they say multimeter. You can measure frequency, you can measure power, you can measure time, frequency, even temperature as well, using a multimeter. Okay, let's look at metric prefixes. When we talk about when you look at the study of electricity, electronics, and electrical, you will be dealing with quantities which are very, very small, and you will be dealing with quantities which is very big magnitude and very small magnitude. So to represent these quantities, magnitude of these quantities, engineering and scientific notation, metric prefixes are very important to denote that. Like if you have milliamps, you know, you can use the prefix milli, or you have microamps or micro farads or kilo ohms, all this. Okay, that's when metric prefixes are very important. In engineering notation, metric prefixes represent each of the most commonly used powers of 10. So metric prefixes like femto, the symbol is F. The power of 10 is 10 raised to negative 15. 1 quadrillionth. Pico, we have P, 10 raised to negative 12. 1 trillionth. Nano, we have N, 10 raised to 9. 1 billionth. Micro, mu, that sign there looks like a U there, it's called a mu. 10 raised to 6 is 1 millionth. Milli, M, 10 raised to negative 3, 1000th. And then we have kilo, K, 10 raised to 3, 1000. Mega, capital letter M, 10 raised to 6, that's 1 million. Giga, that's capital letter G, 10 raised to 9, 1 billion. And then we have tera, T, 10 raised to 12. So these prefixes are very, very useful when you are dealing with physical quantities and their magnitude. If it is very, very small, you use these femto, pico, nano, micro. If it is very, very big, then we use kilo, mega, and all this. So this is how useful the metric prefixes are. Okay, let's look at some of the example here. Express each quantity using a metric prefix. Example 1, that's the example there. A, we have 50,000 volts there, and then we have 25 million ohms, and then we have 0.00036 m. So instead of mentioning this all magnitude there or pronouncing all the magnitudes, we can just use the metric prefixes. Like we can say 50 kilovolts. We can have for the 25 million ohms there, we can say 25 times 10 raised to 6 ohms, or you can say 20 mega ohms. Or for that 0.00036 amps there, it's a long sentence of numbers there. Instead of mentioning everything, we can say 36 milliamps. Okay, so this is how useful the metric prefixes are. You can also use these prefixes to convert 4,500 millivolts microvolts to millivolts. So you can use these metric prefixes. We have 4,500 microvolts is equals to 4,500 times 10 raised to negative 6 volts. It's also equals to 4.5 times 10 raised to negative 3 is equals to 4.5 millivolts. Okay, so another example down there, you see add 15 milliamps and 800 microamps and express the result in milliamps. So you see the example there, convert 8,000 microamps to 8 milliamps, and then you can add. So in order to add such quantities or magnitude of the quantities in different prefixes, you just change one to another, so there is a uniform of prefixes there, like milli to micro, and then you can add the micro, or from micro to milli, and you can add the milli. So these are some of the examples there. Just follow through these examples here to see how metric prefixes are used in science and engineering to represent magnitudes of physical quantities like ohms, volts, resistance, voltage, and current, and all this, especially when they are bigger or when they are smaller. Electrical symbols. In the study of electricity, electrical and electricity, symbols are very important, because in this study of electricity and electronics, circuits or drawing schematics are used oftenly, and you must be familiar with the types of symbols used. The first one is a resistor symbol. We have inductor, which is a coil of wire. Inductor is a coil of wire. And then we have capacitor. Capacitor symbol is two equal dielectric plates. Diode, you see an arrow and a crossbar there, diode symbol. And then switch, see that switch there. And then we have fuse. We have alternating current, AC sign, AC wave in a circle. And then we have direct current, two straight lines there. We have ammeter symbol, a circle and an A in there. Voltmeter, V in a symbol. Voltmeter, W in a circle there. and then we have grounding symbol there, and then we have transformer when 2 coil of wire, and then we have a ferromagnetic material in there, and that's a transformer. We have circuit breaker symbol there. You have a cell symbol or battery symbol. When you have 2 cells put together, you have a battery. So battery are made up of 2 different cells. And then we have electric lamp symbol, X in the circle there. We have electric motor, M in the circle. You have relay and electric wire symbol, straight line. So these are electrical symbol. Later when we talk about circuits, we are going to look at different types of symbol as well, and different types of symbol used for one component like resistor or inductor or fuse. All these, they have other representation of symbols as well in the circuit, so we're gonna discuss more about that. Okay, now when we talk about electricity, electronics, and electrical, safety is very important and paramount. Let's look at some of the basic safety measures in the study of electricity and electronics. There are many practical things that you should do when you work with electrical and electronic equipment. Some important precautions are listed here. Do not work alone. When you are working with electricity, don't work alone. A telephone should be available for emergencies when you are working with doing electrical work. Do not work when tired or taking medications that make you dozy. Okay, so remove rings, watches, and other metallic jewelry when you work on circuits because they are conductors. Do not work on equipment until you know proper procedures and are aware of potential hazards. Make sure power cords are in good conditions and grounding pins are not missing or bent. So it's talking about the plug of the cords. Make sure you must have ground, neutral, and live present there. Keep your tools properly maintained. Make sure the insulation on metal tools and tool handles is in good condition. Especially electrical tools, they are insulated. Make sure these insulation are in good condition, otherwise you might be electrocuted. Handle tools properly and maintain a neat work area. Okay, wear safety glasses when appropriate, particularly when soldering and clipping wires, because sparks might damage your eyes. Always shut off power and discharge capacitors before you touch any part of a circuit with your hands. Capacitors, they store charge. Later when you look at capacitor, you will understand that they are also like a battery. They store electric charge, and if you don't discharge them, then they will discharge on you. You will be electrocuted, they will be shot on your finger or your body. Note the location of the emergency power off switch and emergency exits, especially when you are working with electricity. Never try to override or tamper with safety devices such as an interlock switch or ground pin or a 3-prong plug. Okay, always wear shoes and keep them dry. Do not stand on metal or wet floors when working on electrical circuits, because water is a conductor. So if it comes in contact with live circuit, then current will flow. Never handle instruments when your hands are wet. That's also related to this. And never assume that the circuit is off. Double check it with a reliable meter before handling. When you are working with circuit, especially live circuit in especially maintenance, or when you are doing repair, all this, always test to check that the circuit is dead, meaning current is not running through the circuit. So don't just go and then assume that the circuit is dead. You test using multimeter or appropriate test equipment and see that if the circuit is dead now, it's safe to work. Otherwise, if the circuit is live, you might be electrocuted. It's one of the very important safety measures in electrical and electricity. Some devices such as capacitors can store a lethal charge for long periods after power is removed. Like what I've said, they must be properly discharged before you work with them. When making circuit connections, always make the connection to the point with the highest voltage as your last step. So always do connections of all the necessary connection, but connection of the high voltage, meaning connection like connection to the main supply or tapping into the supply or something like that, it's high voltage. So make sure you do that, make that the last step, or do that after every connection is done in the circuit. Okay, avoid contact with the terminals of power supply. That's also very important. Avoid contact with the terminals of power supply. So these are the basic electrical safety. There are a lot of safety measures, but we are also covering it in this course here. But later you can, when you want to go into more specialized course on electricity, electrical engineering, electrical trade, all this, that's when we take this safety seriously. But these are some of the basic safety that you must take precaution of. Always use wires with insulation and connectors of clips with insulating shrouds. Keep cables and wires as short as possible. Connect polarized components properly. Report any unsafe condition. Be aware of and follow all workplace and laboratory rules. Do not have drinks or food near equipment, especially for electronic equipment. Water and drinks. Water is one of the enemy of electronic components. If water gets into electronic devices, then the device will, if it destroy a circuit board, then your device will not work anymore. So be cautious about that. It's one of the safety for especially electronics. If another person cannot let go of an energized conductor, switch the power off immediately. Okay, that's to do with electrocution. If that is not possible, use any available conductors material to try to separate the body from the contact. So when someone is electrocuted, you don't go and hold that person and pull him away. You use another conductor, otherwise you might be electrocuted as well. Using a lockout takeout procedure to avoid someone turning power on while you are working on a circuit. So lockout takeout is one of the very important emphasis we used to make to our electrical students, because it's very important. Imagine you are working on a live circuit and someone switch on the you are working on a dead circuit and someone switch on the power. That's when, without knowing that someone is switching on the power, you are on the other side working on the dead circuit, but the circuit is live again because someone has switch on the power. So you will be electrocuted. So the best thing to do is switch off the main switch and you tag it, saying that maintenance is going on, or some sort of note that if someone comes there, she will know that maintenance work is going on in that particular circuit. So this is one of the very important emphasis we used to make to our students, especially electrical students. Okay, when we come in contact with live circuit, and when we are exposed to certain current level, we will experience certain physical effects. So this is a table that shows us the level of different current levels and effects that we are going to feel, the physical effects. So on the other side we have current in milliamps, and we have all the physical effects on the other side. So we have 0.4 milliamps. The effect is slight sensation. You will just feel some small effect. 1.1 milliamps, we have perception threshold, meaning slight intensity of the current that we are going to have when you come in contact with 1.1 milliamps. We also have 1.8 milliamps. If we come in contact with 1.8 milliamps, we will be experiencing shock, no pain, no loss or muscular control. 9 milliamps, painful shock, no loss of muscular control. 16 milliamps, we will have painful shock, and then that's when we will the threshold, we will exceed this threshold of intensity, and then 23 milliamps we are going to experience severe painful shock, muscular contraction, breathing difficulty. And then if we are exposed to 75 milliamps or more, then it's gonna be ventricular fibrillation threshold. That's when we start to stop breathing. Okay, feel some difficulty in breathing. Okay, and then 23 to the 233 milliamps and above, or 35 milliamps and above, we will have ventricular fibrillation, usually fatal for duration of 5 seconds or more. And then when we are exposed to 4000 milliamps and above, we will be experiencing heart paralysis, no ventricular fibrillation. And if we are exposed to 5000 milliamps and above, that's when our tissue will start to bend. So these are some of the physical effects of current on our body if we come in contact with live circuit. So we must be always safety conscious when you are working with electricity. Thank you. I think that brings us to the end of our presentation on Unit 1. We will continue with Unit 2 the next time, but please make sure you post your comments in the comment section if you have any questions regarding this unit, Unit 1 of electricity and electronics.